All right, let's get up to Julius.
Can everyone hear me?
Yeah.
Yeah. Hi. Good. Thanks everyone for coming out. Tonight I wanted to talk about a project called SpaceCraft that I built with two other remote developers as a team. This has been quite a journey for the past few months, and the whole goal of the project was to build a real-time collaborative graph. And so I'm going to just show you what the project is, and I'm going to go through the entire process that we went through to build it. So, what is SpaceCraft? So SpaceCraft is a project that we built, which is an open source, real-time collaborative graph. The goal is to write and execute Ruby, JavaScript, and Python code in the browser. It's built with Node.js and uses WebSockets to communicate, and we deploy via Docker. I'm going to go into how each of those pieces fit in. And the whole goal of the project is to encourage pair programming amongst remote developers. So we want to kind of eliminate that burden of having to download language and get everything configured on your local machine and have your other collaborators get everything configured right. We just wanted to create a space for developers to hop into a session and just code away. So I'm going to give you a quick demo of what it looks like. And so this is what it looks like full screen. We have Ruby right now, and we can just create ring. And then we can also, right here on the right side actually, is our code editor. Huh? Oh, the font bigger. Is that it? Yeah. Alright. And then down here in our text editor portion, we can actually just use it and hit run to submit the code. So we can say it's actually loaded within the REPL on the top part, and we can just call that method. And actually what we can see here is I've been collaborating all this time in another session as well on the left here. So let's go ahead and switch to JavaScript. And the REPL actually clears, and we can then just do everything at the bottom there. And every key press gets synchronized across all remote collaborating users. So I'll provide a link so y'all can work with the demo later, but that was just to give you an idea of what it looks like. And before I go into everything about the project, I just want to mention that there's two existing solutions already in the space. I don't know if any of y'all have worked with either of these, but REPL.it is a website that has a bunch of languages that you can pick and try out. There's a text editor portion and a terminal session as well. They're actually trying to go toward making like a whole collaborative environment, an IDE, and they actually allow you to have multiple files and you can require them within the project. So it's actually kind of allowing users to not have any kind of editor on their system. They can just go to REPL and work from there. Whereas CodePad is mainly for interviews, with like recording the phone call and the session as well. Neither of these are open source, and that was one thing we wanted to do, was just create something open source that others can then take and go and run with. Just want to mention that. And for our project, the high-level goals were to enable a terminal-like interface for code evaluation in, right now, Ruby, JavaScript, and Python, with more languages down the road. I want to allow multiple users to collaborate on the same REPL, and we want to synchronize the displays amongst users in real time. But along with this, and going through the journey, we came across some other challenges. And one is that we needed to isolate each session from one another. We didn't want anyone to join another person's session. We wanted it to be where I create a session, and I'm only inviting these other people to my session. Because we have a terminal, and it's actually connected to the back end for our project, we need to prevent any malicious code comes in to affect our host system and allow attackers to then mess with any other users who are using our system. And we wanted to achieve real-time code evaluation and synchronization with no noticeable lag, because any kind of lag is just going to create a poor user experience when they collaborate. And so the way that I wanted to structure this talk was to just go really high level and talk about our architecture. And when that's done, we'll go into building the REPL, and then we'll go one step further down into just how we handle all that security issues with Docker. So the technical requirements for our architecture was that we wanted to be scalable, because we wanted to handle multiple runtimes for every session. Our goal was to allow 3 to 5 users to collaborate in the same session together. We want to detect when a client disconnects to free up resources. And the reason for that is that we didn't want to connect a new user to a session that's been vacated by other users, because they may have some state stored in the REPL, may have just some stuff left over. We wanted to just completely give them a blank slate. And then we wanted to have, we need bi-directional communication, because we're going to be handling a lot of volume from the client to the server, with just all the collaborating users typing away, and then how all the output as well from when users submit code for evaluation. And so we just chose a simple client-server architecture, where all the users will just connect to a central server. And now we come to this question of, where do we want to execute the code? Do we want to execute it on the client side or on the server side? And initially, we thought the client side was pretty attractive. Just, have all of the runtimes and everything on the client side, and with this approach, there'll be just this minimal latency between I'm submitting something for execution and I'm going to get some output back. But there's actually quite a few problems with running on the client side. First is that we have the burden of running an in-browser compiler, which actually, in our experience, slowed and at times hung the browser. And it's not really scalable, because there's a storage requirement for every runtime, about 50 megabytes per language that we found. And since we, in the future, would like to have maybe 5, 7, 10 languages supported, this is just going to grow out of control, and it's not feasible for the client side. And also, not all languages currently come with an in-browser compiler. So we didn't want to add that burden onto ourselves. And actually, this is something that's mentioned by Vincent Wu, the founder of CodePad. He gave this segment, this little piece in the interview, where he just said that one day I sucked it up and I just realized there's no way I could scale this completely in browser execution as far as I wanted it to. And he's like, what are you going to do? Compile every language into JavaScript? Good luck with that. So since he already did that path, we decided to try something else. And we ultimately ended up with executing code on the server side. And we found that this is easier to manage all the multiple runtimes. It's more scalable, because the server storage, memory, and CPU are more readily available than our clients. But at the end of the day, there's also trade-offs. We have to efficiently manage our server resources. There's some increased latency, and it is more costly for us because we have to pay for all that. But we decided that's acceptable. And now we come to talking about how we communicate between this client and server. And originally, we wanted to just go with HTTP. But we found that there's multiple issues that were coming up with using HTTP, and spoiler, we solved these with WebSockets. But the first one that came off of that was the header payload. With HTTP, we were having around 200 bytes for the payload, and considering all the traffic that we talked about between the client to the server and back, we just felt like this was an area to optimize and find something better. Whereas with WebSockets, after you have this initial HTTP handshake to set up the WebSockets connection, you have a full duplex persistent connection between the client and server, and the payload drops at about 10 bytes. So that's already pretty great. And then there's several other reasons why we chose WebSockets. First is that we get a large number of persistent connections between our clients and server. Basically around 1024. And then we can easily detect client disconnection to initiate tearing down our sessions and free up resources. With HTTP, if the client dropped from a session, then we're just kind of wondering what's going on, and we would have to have the server ping that client and say, are you still there? before we can initiate tearing down each session. And that just takes too long. We wanted something instantaneous. With WebSockets, there's actually an event that can fire when the client disconnects. And so all clients from the session disconnect. We can say, okay, tear down the session, make a new one. And now we can get into building a REPL. So this is a typical interaction you have with a REPL on your machine. Whether IRB with Ruby or Node, you're just a user submitting input to your terminal, it's getting read to the REPL program, it's writing back, and then you get your output. But our situation is more complex. We have a user who's submitting input through the browser, and then the browser is sending that through WebSockets to the application server, and then the application server is supposed to talk to the REPL program. But there's a missing piece here, in that we have to have application server logic speak to the REPL program. And there's actually 3 approaches that we came to work with this. I'm going to go through each of them real quick. So the first is we could obviously work with the language's REPL module. Node.js has a REPL module, and we can integrate that in our application code. But now we have some problems because since we're handling multiple languages, and in the future we want to have many, many more, it's going to be difficult to integrate with all the different REPL modules over time. So it's not scalable as we have to rewrite our application code for each supported language. So we just felt like this was not going to work for us. So then the next approach was, okay, well, we can access the standard streams for REPL process. We can have our application spawn a REPL program. We can write the standard input to the program, and then read from the standard output. But the problem with this, though, is that we can have times where either stream gets blocked. And this ends up having some hanging outputs, which is causing a poor user experience. So streams can be blocked, they can lead to hanging outputs, and it's not scalable because the techniques to unblock streams differ from language to language. So once again, we have the issue where we're trying to support multiple languages, but it's biting us in the butt because we just have to deal with every language at that time. So the complexity of our whole project increases for each additional language we want to support. So that didn't work. So we came to our last approach, which was pseudo-terminals. And if we remember our diagram, we have this missing piece here between the application server and our REPL program. And we're trying to figure out a way to send input to the program and get the output. And it turns out that missing piece can be filled with a pseudo-terminal. And the pseudo-terminal basically acts as a communication channel between the application server and the REPL program. And basically, a pseudo-terminal just translates input and output to our REPL program, and it serves as a communication channel. And the reason why we need this is because a REPL program is a terminal-oriented program. It knows how to talk to a terminal, but when you try and just use like our application server code, it doesn't know what to do. So actually having a pseudo-terminal persuades the REPL program, okay, I'm speaking to a terminal, I know what to do, I'll read your input and I'll send you your output. And in case you all never heard about a pseudo-terminal, I actually didn't know about them before I started this project, but they're actually pretty common and we use them almost every day in our life as a developer. There are terminal emulators that fire up a pseudo-terminal background, and Secure Shell uses pseudo-terminals. When you SSH into a remote host, to communicate with all those processes on the remote host, you actually have to create a pseudo-terminal, and then it speaks to those processes for you. So, kind of out there, but it's used everywhere. And so the advantage of this is that we get to offload the burden of managing input and output streams, different runtimes, and we get to reduce our code complexity. It standardizes the way that our REPLs are connected to our code, and it increases our extensibility for any future languages. We can send control sequences like Control-C to stop any kind of accidental infinite loop that someone puts in, and we can capture full outputs like syntax coloring, which is really nice for the user. The trade-off is that we have some increased overhead processing right there on that remote side, but with our experience in testing, it didn't cause any kind of a bad user experience. It seemed to work pretty great. So now we'll get into collaboration, just syncing all that output and input. So let's talk about output. Let's say the client submits some code to be evaluated, and it sends to the app server. The app server then sends that to the pseudo terminal, which we just condensed to pseudo terminal REPL for the image. Well, the app server will then receive the output from the REPL program, and it's going to broadcast it to all the clients through WebSockets. And then everyone has the same display. As for input, let's go through the steps. Let's say a user presses the key, like the open square bracket. It gets stored in some state to basically say what's on the line. And for every key press this is happening, it sends that updated line to the app server. And then the app server is going to parse out the current prompt from the output cache. And then it's going to broadcast the prompt from the line to all of your collaborating clients. And then everyone has the same display. Now, as when you work with any kind of collaborating product, Google Docs and such, there's going to be some conflicts that occur because sometimes one or two more people are going to be typing on the same line at the same time. And so we have to handle those conflicts with shared editing. So like I said, multiple people could be typing at the same time, or our server may receive updates in a different order than they were sent. And if those conflicts are left unresolved, then the clients aren't going to converge to the same state. So I might send something, get back something, but the person I'm supposed to be collaborating with will get something different, and then we don't know what's going on. So we have to handle it in two spots, in our terminal and in our text editor. So we'll talk about the terminal first. And what we actually chose for the terminal was eventual consistency, or the last write wins. So when multiple people are trying to edit the same line, and the server receives all those updates, it's going to pick the last one that was sent in. The advantage of this is there's less server overhead. The server isn't trying to perform some operations, trying to figure out, okay, let me just try and take all these updates and make it into something that works. I'm just going to pick the last one. And this actually reduces our code complexity by a lot. The disadvantage is, I might overwrite someone who wrote before me. But we feel like this is acceptable for the terminal because the terminal is where you're trying to send something for evaluation, you're trying to store some state. It's not somewhere you effectively collaborate a lot in. You only have one line at a time. So we expect all users to be like good agents and basically saying, I'm going to put something in the terminal right now, don't touch it. And so we can see here that we have two clients. Client 1 sends a line with the character A, and they get to the app server first. Client 2 sends character B, and they come in a little bit later. And so the server's going to receive line A, then it's going to receive the line B, and it's going to pick B because it's the last one, and everyone gets updated. Now let's talk about the text editor. And this one is more complex because you have more space, and it's feasible that I'm partnering with someone, and maybe I'm writing a class up here, and they're doing some other stuff below, and then maybe someone sees a typo, and two people try and fix it at the same time. It's an area that's more ripe for these kind of conflicts. And you can kind of see here what it can look like. We have the same state on both sides, a string of 18, and let's say client 1 tries to insert a character at the beginning because they want cat. I want my string to be cat. But client 2 says, no, actually, I want to delete character A. Let's go ahead and do that, and I want to end up with T. Well, locally, they're going to get what they want. But then when it gets sent to the app server, it's then going to send those operations to the others, and they're going to receive it, and you're going to end up with not what you want, nor anything that's synchronized. And that's just not at all what we want. So for this, we actually chose to offload it to YJS, which is a shared editing framework that uses what's called a conflict-free replicated data type, or CRDT. They're pretty complicated, and basically what they do is they receive all these updates, they perform some operations, and they say, okay, I'm going to insert everything where it needs to be, and give you the exact same display. So then, when you do this, when you use the CRDT, your concurrent edits converge to the same result, and it doesn't matter what order they're applied. So we then get conflict-free real-time editing just as a result. And the trade-off is we have some increased memory usage on the server side and increased bandwidth. And the reason we chose to use a framework to handle this is, like I said, CRDTs are pretty complex. There's some projects that take whole teams and months just to get them right for the project, and that's not something that we wanted to take on for the project. We wanted to focus on the REPL and the REPL experience, so we were happy to let YJS do this for us. And so now we'll get to the nitty-gritty at the base with using containers to deploy with our application. And so in the beginning, I was talking about how we had some problems come up with the application. And first was potential malicious code being input by users. Users can enter that into the system, something like a dirty cow or copy and write exploit, which gives attackers root access and then compromise their host system. They can then have free reign to do anything they want with our users. So there's that problem. And then there's resource sharing. We have all these users, they have their own sessions, they're writing code to evaluate. One user maybe writes this whole program that's very computationally intensive, or another user just does this really huge loop that just is going to crunch away. And if we don't figure out a way to share resources, one session is going to hog away all of the resources from all the other sessions, and that's going to be a really poor experience because everyone else's performance is just going to drop. And so we have to figure out how to handle these two cases. And so we did use Docker and containers for this, but before I get into that, just in case, I don't want to assume everyone has used containers before, so I'll just do a quick slide on what containers are. A container is basically an encapsulated unit of software that can contain an entire service, contain all your dependencies for maybe a development environment. It's basically just a box, you put all your dependencies in, and it's isolated from your host system. So you don't have to worry about managing all these different kinds of versions or configurations. You can hop in your container and work in there. And containers are built from images. So an image is just a file, it's a snapshot of everything in a container, and then you can create containers from them. And so you can see here what I'm talking about. We have our image with what kind of operating system we're using, our app code, our language runtimes, and then we can create containers based on that image from there. And so why containers? With containers, we get some isolation between each of our sessions. We basically have a whole copy of our app in each container. And the file systems in those containers are self-contained. Users will not have access to the host system on our server by default. Containers have a lower footprint than virtual machines. For our project, our containers had around 50 megabytes in the beginning before any user started submitting anything to the state, to create some state. But virtual machines would be gigabytes. And just for scaling, we felt that having that low footprint was really helpful. Containers by themselves aren't entirely secure, but you can make them secure with some extra measures. And lastly, all those hogging of resources that I talked about, well, they can be limited with seekers, also known as control groups. So I could set the containers to be built with, you can only have 100 megabytes of memory that you can use, and you can only use at most 20% of the CPU of the server. That's all you're going to get. And then no matter what they try and run in that container, they're not going to get any more. And so you can see this diagram of this. We have 3 containers, each with their application in there, and the middle one gets compromised. Some code gets sent, or they're trying to hog all the resources, but it doesn't work. It just gets isolated away, and everyone else is still happy in their sections. So, like I said, containers by themselves aren't really secure, but we can make them more secure. So applications run in containers and can access system resources on the host system because they speak to the host system to make system calls with the host kernel. So a particularly persistent or crafty hacker could find a way to escape out of that container and then have access to the host system. And so here's what we have right now. We have the app in a container. They can make system calls to the host kernel, and there's very weak isolation. And we want to try and strengthen that there, while also trying to take away some of the abilities of someone within the container. There we go. So first step, we can secure the containers by making a new unprivileged user profile. So any user, any client that connects to a container for their session, they're going to run as an unprivileged user. And then we can just limit any kind of actions they can have in that container. They could type rm rf-home directory and all day, and it's not going to affect our container at all. Then we can also add a container runtime sandbox. And what this does is it runs an instance of this for every container, and it provides some isolation between the container and the host kernel. And it basically intercepts all those system calls. And it acts as a good guest kernel with unprivileged access. So basically, it just provides that strong isolation so that anyone that tries to escape can't get to the system by itself. The trade-off is this is a higher memory consumption. So, like I said, our containers started off around 50 megabytes in memory. And when we used our sandbox, it was around the same. So on a 4 gigabyte RAM server, we could run 50 containers with the sandbox. But if we decided to take away the sandbox and just run the containers, we could run up to 100 on the same size. Just depends on how safe you want to be. And so now we have an updated diagram with the container, and now we have this sandbox in between intercepts to the host kernel. And we use gvisor, which is an open source sandbox from Google. And now we're at the home stretch, which is we have everything, but now we need to connect users to our containers. And the naive approach is we can just use port forwarding. We can forward a request from one host and port number to another. We can just map a user's request to the unique IP address and port of a container, and we're all good to go. And you can see here a table of that. We have 3 sessions, each with a port number on the host and connected to a container. But this isn't a good design. There's really no privacy with this because anyone using port scanner can just find open ports and then just hop into someone else's session and just start messing around. In fact, if you just found out that you're on port 5000, you could just freely try 5001, 5002, and so forth. So this isn't providing any kind of privacy. So we ended up using a reverse proxy to help solve this problem. So we set up a web server as a reverse proxy, and it serves as an intermediary between clients and the server. So we basically abstract away all that connecting of the IP addresses and the ports by assigning a random session ID every time we make a new session. So there's none of that clear mapping, it's abstracted away. And this ensures the privacy. Our session ID is going to be a lot harder for anyone to just randomly guess and find out. And then as a bonus, always trying to look forward, as our application scales, the reverse proxy can act as a load balancer if we add more servers or can cache some content for us. And so now we can see this updated table with our session IDs at the front and each one. And these are going to be a lot harder for someone to try and just randomly guess. And just to give like a diagram of how this connection happens, a client requests to get a session of SpaceCraft, reverse proxy catches that, and then speaks to the server. The server says, okay, here's the container IP and port, and the reverse proxy then forwards the client to that container. And then once the client and container complete that HTTP handshake, they're connected to WebSockets for the remainder of the communication. And then, like I said earlier, when that last client from a session disconnects and there's no more clients using that container, then we just tear down that container. And now we get to future work. So our team is looking to do a few more things to the project. We want to add some remote cursors for user identification in the text editor. Something like Google Docs where you have like a name and a color and everything, just so that it's more visually clear where everyone is in the text editor. We want to potentially enable users to just download code from the editor, save it, and then put it back up there for later. We want to add more languages. Something kind of exciting like Rust, Go, Crystal, Haskell. But for these low-level languages, we will have to find out a way to handle them. And then lastly, implementing a request queue just to handle a large volume of requests. And that's my presentation. So here's my contact info, and here's the GitHub for the project. And you can visit SpaceCraft.com to see the demo. And now I'm ready for questions.
So how do you prevent someone from doing an infinite loop? You said that you can Control-C, but how do you capture that Control-C?
Sorry, how do you do it?
How do you capture it? So like if I'm on a Linux machine, I'm going to copy some code. I don't want to quit the REPL. So how do you handle that?
So what you mean is, let me see. So let's just do.
You could just use like Linux resource limits, like the limits command. You can specify that like you can only run, you can only use the CPU for like so many seconds or whatever.
And that won't happen. That's not something we implemented. We just, if you're doing an infinite loop and you're in the REPL, then you can just hit Control-C and we capture that. And Xterm is the terminal emulator that we have. That one actually also has a method built in that will capture any kind of control sequences that you want.
Okay, so if I want to copy some text, it won't actually quit the process that's running, or it will.
Let's see.
So like if you have something on the left terminal that's printing, and then on the right terminal I'm going to capture the output, and I'll say, oh, like, here's a string, I want to copy that.
You're saying so left terminal, right terminal, so you're talking about like two?
I'm sorry, like this session that you have up here.
Oh, okay.
Yeah. So like if on the left side, you run something, you run a command, I just want to copy that output. That you, like, I want to copy hello world. Like you're still printing hello world and something, like I just want to copy it. That's all I was asking, is how do you prevent that?
The question before is, are you passing signals through that? Like you're not detecting something, just Control-C and then sending a control signal?
No, like right now we just have Control-C.
You do or you don't?
Yeah, right now we just have Control-C for if you have a
So if I'm in Linux, I want to copy code, I can't.
Not right now.
Okay.
Just took a second.
Second question?
Yeah.
How come you chose Ubuntu instead of Alpine?
So we actually started off with Alpine. And we had that because, it's obviously more lightweight, less memory footprint for the containers. But after a while, we just were having a lot of bugs with the whole program. We were just not getting anything actually sent to the server for evaluation. We were getting like hanging output and everything. And we were just trying to debug it for a long time. And we just had a discussion after a while of like, well, we could probably spend another, I don't know how much one time trying to fix it, or we could just try and switch to another one and see if we don't have the same problem. And we just switched to Ubuntu and it was fine. So, that's not like, I want to know why I did that, but just to kind of move forward the project at the time, we just switched it and fixed it.
Okay.
Yeah. But, that is what a lot of people do, just like Alpine's so much smaller.
But it's a hardened kernel, so you would have not had to use that gvisor then by using Ubuntu. Like it's hardened, it's always updated for attacks. So that's really why I was curious, is why you added an extra layer instead of using a kernel that's pre-built to patch all the exploits.
Yeah. Well, so because this whole project was like a step-by-step process. In the beginning, we were just getting set up with Docker. We just chose Alpine because it's smaller. We were just like, okay, this is great. We can make more containers on the same server size. And then we had that issue, and we fixed it with Ubuntu. And then later on down the road, when we started to actually figure out how to make it more secure, we were already way past Alpine. We didn't even realize it could have been more hardened in that sense. So,
Okay.
Yeah. But yeah, if we could have gotten it to work, then we could have just phoned you guys up.
You run into the situation that it doesn't use GCC. We've experienced that at my company with WebSockets and things hanging, and we have to compile from source. Or I'm sorry, use the muscle instead of it doesn't use GCC or Clang. It uses the muscle.
It's like one of the great issues with being able to install like code and Python dependencies.
Yeah.
That was just failed to install.
You actually have to modify the C code. That's what we do at my company.
You have to modify the dependencies,
No, we actually download everything from source and change libraries or change code, and then we compile it.
That sounds pretty good.
It's actually really simple. The Node is really simple to compile.
The other thing to do is make a challenge on an Alpine-based image and go figure out what libraries would replace the GCC-related logs. Usually you can find the headers that are in some other library.
So that didn't work for us. It was really simple actually. Instead of using OpenSSL, we just use Libra, problem solved. But then the headers change. So you just go modify the code and say, whatever. Different parameters being passed in.
got a question?
Yeah. You have a question first?
Sure. I think like the use case originally proposed is that you wanted to have REPL for remote developers so they can share with each other, right?
Yeah.
So isn't it just easier to use like GitHubs or Screen for that? Because you already have like all the infrastructure for it essentially, right? You just use SSH or Box, right? It's already like you already get like the best latency because there's no extra like middleman, so to speak, right? And you just connect to the same server and you just will both open team ups, right? And
Yeah, but if you're handling like a beginner, I don't know, like both of those solutions are like not something I'm gonna try to deal with. When you're like teaching somebody, you have like a super junior, and it's not really like savvy.
well, but then you would not be hiring a super junior for a remote position in the first place, right?
Yeah, well, so what's this for then?
I think this is, that's my one.
That's it. Is that?
Yeah.
I mean,
He has like,
who's the intended audience?
Oh, sorry. The intended audience is, like, we want anyone to be able to come and use it, but we also did cater to that audience of maybe you're a new or junior developer who isn't quite comfortable with team-ups or something like Linux, like just going full on Linux with everything. But I will be honest that part of this project was for all of us just to try and build something with all these technologies and just have this learning experience with it. There's other great options. We can just teletype with the code editor that you can then collaborate with people. And we just felt that like there's not really an open source solution for someone who doesn't have a lot of programming experience. So it's like, I guess the intended audience, what I did make clear was that maybe you're a newer developer and you don't quite feel comfortable with getting into something like this.
Yeah, two questions. The first one is, how are you leveraging Docker, or like, how does it fit in the architecture?
So the Docker is basically where we have a complete instance of the whole project.
Yeah,
And
I
then,
guess the question is, what's launching Docker? Do you have a process that's like, run fetches, or?
oh, sorry, I see what you mean. So the process I didn't get into, because it's already so many slides, is that when we have our reverse proxy, when the HTTP request comes in to make a new session, then we have a call made to the API on our server that says, okay, create a session. The session is then built up, and then we grab that IP and the port for the container, and we send it from the server to the reverse proxy, and then apps it. So it's the reverse proxy gets the request, and then the container is built up.
Okay, how is the container built up? I guess is the question. Is some route that you call that does like a child process.exec or how it runs?
Yeah.
Okay, cool. Another question was, how many people are working on it? How long have you all been working on it?
So it's myself and 2 other developers. We started it in the first week of October.
And how do you limit the number of sessions? You said you want to limit to 5, but if I have like that little short ID, I can give it to everyone here, and then we all log in.
Gotcha. So the 3 to 5 in the beginning was for each session. Like I wanted 3 to 5 users per session to be supported, but that was just kind of like a baseline. Like we didn't want to have just 1 user, 1 or 2 users. We wanted to make sure that our lower limit was 3 to 5. In testing, we can have up to 10 people.
Oh, wow.
Per session. Yeah. And on our 4 gigabyte, we've had, like I said, 15 gigabytes are up and running and everyone's using it.
More questions?
I have one more question. That's my swear. How low level do you let people get? Like, do you let people spawn threads, like Python threads? Or do y'all block that?
We block that right now.
Okay.
Yeah, just trying to keep it very simple.
Yeah.
Yeah. Only been at it since October.
Cool.
Any other questions?